All right, I'm going to make a video for section 3.7 on related rates, at least a little intro to the idea. That way we can spend time in class working through some homework problems and some examples. Okay, I've been trying to make this video and my dog is being a real pest, so I'm hoping he'll behave this time. All right, so on this one, we're trying to deal with a type of problem called a related rate problem. All right, so related rate problems involve finding rates of change of two or more related variables that are changing with respect to some third variable, like time, typically. All right, now that idea of rate of change, that's the idea of slope, okay? And you know slope is related to derivatives. So that's why it's in chapter 3, because it's related to derivatives. You have to understand how to do a derivative. Now, the other issue that's going to happen is we're going to be dealing with a situation where we might have, say, a formula like this, maybe V equals 4/3 pi r cubed. That formula is the volume of a sphere given the radius. Allows you to get the volume of the sphere if you know the radius. All right, so what's going to happen, what related rate problems do, is we're going to be asked sometimes to find maybe the rate of change of the volume with respect to time. That would be dv dt. Okay, so we might be asked to find that. Okay, what will be given is the rate of change of the radius with respect to time at a particular, at the instant when the radius equals, we'll know, let me put an equals there, we'll know this, for instance, and we'll know a particular radius. So we might be looking for the rate of change of the volume with respect to time. If we know that the radius is changing with respect to time at a given rate when the radius is a certain number of feet or whatever, okay? That's kind of the idea. So what happens is we wind up having to do the derivative of this equation right here on both sides with respect to a third variable, time. So it requires that we use implicit differentiation. That's why this section comes at the end of chapter 3. We can't do it until we know how to do implicit differentiation. Okay, so this paragraph just kind of outlines kind of the idea and the importance of it. So we've talked about how derivative can be used to determine slope. Okay, let me just underline slope. And the derivative can also be used to determine instantaneous rate of change, the rate of change of one variable with respect to another at a given instant. All right, so you'll see these kinds of problems. Sometimes you're dealing with something like population growth or production rates, water flow rates, velocity, acceleration I listed. Okay, but it can even be lots of business applications, like production rates could also be, at what rate is the revenue changing with respect to time if the sales are changing at a given amount, okay, at a certain point in time. All right, let's go ahead and work a problem. I think that's the easiest way to really get the idea of it. Okay, so let's look at this problem. This one is a good one to look at initially. All right, so on this example, we're dropping a pebble into a pond. So when we do that, you know that these concentric circles are going to be formed going out from that where we drop the pebble. So this question is saying the radius of the outer ripple. So the radius, remember, is from the center to the outside of the circle. So that right there I'm talking about as being the radius. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. Okay, that rate at which the radius is changing with respect to time, that's what dr dt is. It's the rate of change of the radius with respect to time. And we're given that. We know it's 1 foot per second. All right, and then it says when the radius is 4 feet, so when r equals 4 feet, at what rate is the total area of the disturbed water changing? So we know this length is growing at a rate of 1 foot per second. So once that radius has reached 4 feet, we're being asked, what is the rate of change of this area, the area of this circle? So that means what we want to know is the rate of change of the area of the circle with respect to time. Okay, so that's kind of the given information of what we're looking for. So your job is to find a formula that you know relates the variables in the problem. So we're talking about the area of a circle. We know that formula probably. If not, there's formulas in the back of your calculus text. We know the area of a circle is pi r squared. All right, so I'm ready to go in and do the derivative of both sides, but I'm doing it with respect to time. So this would be 1, and then the derivative of a would be dA dt. Over here, when I do the derivative, I would get 2 pi r to the first power times the derivative of the rate with respect to time. Okay, so we know this formula, dA dt equals, and I'm just kind of writing it more smushed together, is this. And don't forget that's times there. All right, so then here's the thing. I want to know that, and I'm given, or I know what the radius is, and I know what dr dt is. Okay, so I'm going to take this formula here, and I'm just going to plug in what I know. Let me rewrite the formula real quick, and then I can plug in right below it. All right, so I know my r and I know my dr dt. I want to know what the rate of change is at the instant when the radius is 4. dr dt I was told was 1. So I'm going to get 8 pi. And a lot of times they want it in terms of pi when you're dealing with formulas related to circles and spheres. And so the rate of change of the area with respect to time is 8 pi. And the units on that would turn out to be square feet per second. And that's because the 4 was feet, wasn't it? Okay. And the 1 was feet, was a rate. So it was feet per second. Rates are like miles per hour, feet per second, that type of thing. So you see we have feet times feet would be feet squared per second. All right, so there we have it. Okay. Now sometimes they want you to go on and get a decimal for it. So you would take 8 times pi and give us an estimate. But if you can do it exactly, typically that's what they'll want. All right, so I've included the guidelines here that are in the textbook for that. So look at what you're given, look at what you need to find. If you can draw a sketch, do so. Okay, try to find an equation that relates the areas. I said it wrong. Relates the variables in the problem. Like in our example, it was area of a circle and radius. Okay, then you're going to use the implicit differentiation to differentiate both sides. So this involves the chain rule. You're doing the differentiation with respect to time t. And then at that point, you should be able to substitute and replace everything in that problem except for the one thing you're looking for. Like on ours, we were able to replace everything except for dA dt. We knew this. We knew this. All we needed to find then was dA dt. So we could use basic algebra to do that. Okay? All right, so some of the problems that you're going to be asked to do are like this example. They'll give you an equation that involves, say, y's and x's. This equation is going to be differentiable, and we're going to do it with respect to t on both sides. So we're thinking of both y and x are variables, and we're going to try to go through here and take the derivative, but do it with respect to this third variable, t, typically time, okay? So I'm going to come in here and I'm going to do the derivative of the left side with respect to t. So I'm going to get 1 dy dt. Then I'm going to do the derivative on the right side. So that's going to be 2x dx dt. Got to use the chain rule. Got to bring the power rule, bring the 2 down, get 2x to the first power, and then do the derivative of the inside function with respect to t. Okay? Then when you do the derivative of 3, that's going to be 0. Okay, so dy dt equals 2x dx dt. Okay. All right, now let's look at the two problems that we're going to be asked to do. All right, on this one, we're going to take this formula that we just found, and here we're being asked to find the derivative of y with respect to t. Okay, so we know x is 1. We can replace it with 1, and we know dx dt is 2, so we can replace it with 2. Okay, so we know x is 1 when dx dt is 2. So we plug both of those in, and that formula then tells us that dy dt would be 4, and that would be your answer. Okay. On this one, we start with the same formula. Okay. But then what we know here is that dy dt is 12 when x equals 3. So you plug that in, and see up here, the unknown was on this side. On this one, the thing I'm looking for, the unknown, is on that side. So I'm going to have to use a little more algebra than I did on the other one. That would be 6 dx dt. Okay. And I want to get that dx dt by itself. So I'm going to divide by 6 on both sides. And that gives me that dx dt would be 2. So the answer to the question would be 2. Okay, so a lot of the questions are like that. It's like questions 3 through 6 when you do those. Actually, 3 through 10 in the text are all kind of like that. All right, and then let's do one more that's a little more, involves a little bit more, just so you get a sense of it. And then I want you, when you finish your test, I want you to go in and take a look at those homeworks. Let me get a little more paper just in case. All right, so let's read through this question, see if we can figure out what's going on here. All right, we've got sand being delivered to the site of a new building. Sand is falling off the truck into a conical pile. So immediately I want to draw a cone. Okay, there's my cone. Okay, circular base, and then it goes up to a point. All right, and we know that the conical pile is falling off the truck into a conical pile at a rate of 10 cubic feet per minute. So that has to do with the volume that this pile. It's falling off the truck at 10 cubic feet per minute. The pile is growing at a rate of 10 cubic feet per minute. And in cubic feet, that's a volume. So we know dV dt is 10 cubic feet per minute. Okay. All right. Then it tells us that the diameter of the base of the cone is approximately 3 times the altitude. All right, so just some terminology. The altitude is the height of the cone. Like that's this. Okay, the perpendicular distance from the top to the base. That's the height right there. The altitude or the height. Okay, the diameter, remember diameter is from one edge all the way through the center to the other edge of the circle up that forms the base. So we know the diameter, and I'm going to write it out in words so it doesn't look like the D I've been using. We know the diameter is about 3 times the altitude. I'm using H to stand for altitude or height. All right, then it goes on to say, at what rate is the height of the pile changing? At what rate is the height of the pile changing with respect to time? That's dH dt. That's what I'm looking for. Okay. When the pile is 15 feet high. So when h equals 15 feet. All right, so I've kind of extracted what I could out of that problem. Now, they suggest that we use this formula. Volume equals 1/3 pi r squared h. 1/3 the area of the base times the height. H, not pi. Let me write that better. Okay. All right, so the thing is, there's too many variables in there, okay? See, I've got one rate that involves volume and one rate that involves the height. I don't have any rate involving the radius, So I need to try to rewrite this formula so it only has V's and H's. And I'm going to be using this information to do that. Okay, so let's think about that. The diameter is about 3 times the height. Now the diameter is all the way across the circle, but remember a radius would be just from the center to the outside. So the radius can be used to the 2 times the radius could be used for the diameter, couldn't it? I'm trying to get the R out of that problem. So here's how I'm going to do it. I know the radius is about 3/2 your height. I just divided by 2 here to get that. So what that's going to allow me to do is to plug in 3/2 h right here for the R. So 1/3 pi 3/2 h squared times h would equal my V. Now we got a little cleaning up to do, and this problem can get a little messy. I wish I had my calculator with me. I don't. Oh well. So you can do a lot of your fraction work on the calculator if you need to. This one's not too bad to start with. That would be 1/3 times pi times 9/4, 3 squared over 2 squared, times h squared times another h. Okay, so my formula kind of transforms when I put these together. That would be 3/4. We have a pi, and we have h to the 3rd power. Okay, so there's my formula cleaned up so it has just h. I got the r out of the mix, and I could only do that because they gave me that extra little statement in the words of the problem. All right, so our job now is going to be plug in what we know. No, it's not yet, sorry. Our job now is going to be to go on, and at this point, I'm going to do the derivative of both sides with respect to time. So the derivative of the volume with respect to time, okay, would equal 3 times 3/4 pi h squared times the derivative of h with respect to time. Doing both sides with respect to time. Okay, so the derivative of the volume, that was to the 1st power, so it was 1 dv dt. And then over here, we had all this other stuff. All right, so simplifying that formula before we plug in, I'd get 9/4 pi h squared dh dt. Okay. All right, so here's my known information. I know this, it's 10. I know this is 15. Pi is not a variable. Okay, so I only have one unknown, and that's dh dt. So you're going to plug in 10 here and 15 there, and then you're going to wind up solving that for dh dt. Okay, so that would equal 9/4 pi 15 squared dh dt. All right, so let me do some algebra on this. Okay, so all of this, when you collect it together, you would take your 15 squared, that's your 225, multiplied by 9. Okay, you would get 2025 times the pi over 4. That's what you have on that right-hand side. Over on the left, you have 10. All right, you're trying to get this by itself. Sometimes people do better when the unknown is on the left to start with. So let's just interchange those two sides because this is messier than we typically get. So if I want this by itself, I could divide by 2025 pi. Actually, I like to do it. Can I just show you the easier way so I don't have to get you to use a calculator? Just clear the denominator out, multiply through by 4. See how that's going to give you 2025 pi times the dh dt is equal to 40. Then come back in and get rid of that 2025 pi on both sides. Okay, so the dh dt rate would be 40 over 2025 pi. All right, now it turns out I can do a little bit of simplifying because both 40 and 2025 are divisible by 5. So that would be 8 over 405 pi. Okay, so that would be the rate of change of the height with respect to time with the pi in there. And then if you divide 8 by 405 pi, make sure that you're dividing by all of that when you do it. Make sure you type it in 8 divided by all of that. Okay. What you wind up with is that turning out to be about 0.0063. Okay. Now let's talk units a little bit. The units here need to be a height per time, right? So like up here, the height was in feet, the volume was feet cubed per minute. This is going to turn out to be that many feet per minute. Okay, that's going to be feet per minute if you put the unit on that. And you can let that come out of the units that are on each piece of this when you plug in. So for instance, this is feet cubed per minute, and this is feet. Okay. So you can think about that. When you did all that multiplying right here, you wind up having feet squared because it's 15 times itself. Here you had feet cubed per minute. So when you divide by this quantity right here on both sides, when you get to this point, when you finish that division on both sides, you took feet cubed per minute and you divided by feet squared. That's feet cubed per minute times 1 over feet squared. That knocks out 2 of those, and you just have 1 foot left per minute. Checking on units, I showed you that because sometimes checking on units can help you to get the answer correct. Because if the units don't work out, then you've set it up incorrectly. All right, so that's all I wanted to show you right now. I'm going to adjust the homework a tad. I'd like to add a couple additional ones in it. We'll look at some of these in class. So this will be the new homework that I want you to do. I just added in 15 and 18. And I may also do one that's a business problem that we don't have any in this textbook, but I'll find one that's related to like revenue or something like that. And we'll do a little worksheet on that later.